Hi guys, it's Mrs. Morgan. This will conclude chapter 13, so I recommend that you finish reading um, chapter 13, section 2, and this will take care of the frappies in the last packet, and it's labeled chapter 13.2 frappies. So 13.1 talked about comparing two um, population means, and here we're going to compare two population proportions. So let's just um, remember what we did with proportions. So we had a one prop z interval, and that's exactly what you press in your calculator. And remember that formula was p hat plus or minus z star times the square root of p hat q hat all over n. Um, and I'm just going to write here because the normality condition changes, so I'm going to write that up here as we go along. So the normality condition for, whoops, look at that Y, sorry. The normality condition for this was, remember, it was n times p hat is greater than or equal to 10, and n times q hat is greater than or equal to 10. So that was the one prop z ints. And we use p hat in our standard deviation because when we calculate an interval, we're trying to estimate where the true proportion lies. So you don't know the true proportion, which is why you're using the p hat and calculating a standard error. Okay, so now let's also remember how we did a one prop z test. And again, that's what you press in your calculator. So with testing, we're trying to find evidence against the null. So the test statistic is going to be z equals p hat minus p naught divided by the square root of p naught q naught all over n. Now we use p naught as opposed to p hat because you're testing a claim here. And the normality condition would be n times p naught is greater than or equal to 10, and n times q naught is greater than or equal to 10. So just keep in mind when you do one sample, um, either you do the one prop z int or the one prop z test, that the normality conditions change. Okay, very slightly though, but the SRS and the independence would be the same. So now 13.2 goes over the two prop z interval and the two prop z test. So we're going to dive right in here. The two prop z interval. Now you're comparing two um, population proportions, and you're trying to estimate where the true mean difference lies between the proportions. So again, we use the hats as opposed to the p naughts in this case because we don't know where the true mean difference lies. So here you can see that the normality will also be that n1 times p hat 1 is greater than or equal to 10, and n1 times q hat 1 is greater than or equal to 10. But you have two samples, so we also have to include n2 times p hat 2 is greater than or equal to 10, and n2 times q hat 2 is greater than or equal to 10. Now, the rubrics on the AP for this normality condition, oh no, the rubrics on the AP, my correction, is still greater than or equal to 10. Your textbook is a little different here. They say at least 5. So they're going a little bit more conservative in the textbook, but the AP is using 10. So honestly, it does say in the rubrics 5 or 10, so don't worry about it. Let's just keep the magic number 10 for these normality conditions. Okay, and now the formula for the two prop z test. So we're assuming that the proportions are equal, and we're going to see that the alternative can be that p hat is greater than, I'm sorry, not p hat, p1 is greater than p2, or you could have p1 is less than p2, or you could have the two-sided test where p1 is not different than p2. Okay, so unequal. Okay, so the test statistic here becomes p hat 1 minus p hat 2. Now, the standard deviation for the two-prop z-test is completely different from what we've seen in the past. They calculate something called p hat c, and what p hat c is p hat combined. And really all that is they average the p hats. Well, kind of average, you'll see in a minute. They average the p hats because you don't know which one to go with. You don't know if you go with p hat 1 or p hat 2, so you just go with what's known as p hat combined. All right, and so we're going to dive right into the first FRAPI so you can see actually how we apply all this stuff and check for understanding with what I just went over. So just reading here, I didn't read it. P hat combined equals count of successes in both samples combined over count of individuals in both samples combined. So you can see that that's not a straight average because you're doing p hat 1. No, let me not do it here. Let me do it with numbers because it's going to get confusing if I write it like that. All right, so I'm going to come back to this. These are the conditions, and here we have the conditions too. So the conditions for the, well, actually, I don't have to come back to it. This is like on the cheat sheets that I hand out to you that you put in your folders. I'll give you guys those tomorrow too. You have an SRS. So for this is for the two prop z-ints. So here I'm just reading SRS. We already ran over the formula, okay? The SRS is the two conditions can be viewed as an SRS from their respective populations, or are the two groups in a randomized experiment. So that was the whole idea, that if you're drawing from two separate populations, or is one group getting one treatment and the other group getting the other treatment, therefore they would be random. Now normality here, we went over the normality, I'm not doing that. Independence is the two samples are independent. When sampling without replacement, check that the two populations are at least 10 times as large as their corresponding samples. So again, if you're drawing from two populations, you're going to want to use that n is greater than or equal to 10n for both populations. If it's from an experiment and both are receiving treatments, then you're going to want to just say that if they're randomly assigning the treatments, then the two groups would be independent from each other. So that's the conditions for the two prop z-int. For comparing two proportions in a inference test, so a two prop z-test, this is kind of blurry, but we went over the normality condition, and now the normality condition in your textbook is going to be different. So what I said before, and I will adjust your cheat sheets, you're going to want to use what the rubrics do on the AP. So they're checking N1 P hat 1 is greater than or equal to 10. N1 Q hat 1 is greater than or equal to 10, and then again for the second sample, N2 P hat 2 is greater than or equal to 10, and N2 Q hat 2 is greater than or equal to 10. Okay, now independence. The samples are independent when sampling without replacement. The two population must be at least 10 times as large as the corresponding samples. So again, I sound like a broken record, but if they're coming from an experiment and they're both randomly assigned, then that's good enough to say that the two groups would be independent. But you also want to make sure that if you're drawing from two distinct populations, that each population would be at least 10 times as large as the sample. All right, so we're going to dive into the first FRAPI here. Now, the first FRAPI says a random sample of 415 potential voters was interviewed 3 weeks before the start of a statewide campaign for governor. 223 of the 415 said they favor the new candidate over the incumbent. However, the new candidate made several unfortunate remarks 1 week before the election. Subsequently, a new random sample of 630 potential voters showed that 317 favored the new candidate. Does these data support the conclusion that there was a decrease in voter support for the new candidate after the unfortunate remarks were made? Okay, so it says give appropriate statistical evidence to support your answer. So now again, I know that this is a significance test and not a confidence interval is because they're saying does the data support the conclusion that there was a decrease. So you're checking to see if somebody's like the claim that there actually was a decrease in voter support is actually true. And then give appropriate statistical evidence again says show, when it says that that's the indication to you to do a inference test. Okay, so again, we're going to want to define what p hat 1 is. So p hat 1 is the true proportion of voters who favored the new candidate over the incumbent three weeks before. And p hat 2 is the true proportion of voters who favored the new candidate over the incumbent one week before. Okay, so the null is that these remarks didn't hurt the candidate. However, p hat 1 is 223 over 415. So that was the proportion that favored the new candidate before he made the remarks. P hat 2, whoops, P hat 2 is 317 over 630. So let me just go to my calculator for a minute. 223 divided by 415. The proportion is approximately 54. And let's go 317 divided by 630. And that's giving me 0.50. Okay, so the alternative then makes sense that you would say p hat 1 would be greater than p hat 2 because did the data support the conclusion that there was a decrease in voter support for the new candidate? So a decrease in voter support would mean that the proportion went down. So p hat 2 would be lower than p hat 1, and p hat 1 would be higher. So here again, it's good if we establish a significance level. Here we'll say alpha is 0.05. Okay, and now we want to go through the conditions. So again, the SRS, both samples are random. Normality, like I said, a lot of times actually, The normality condition is that you're going to want to say N1 P hat 1 is greater than or equal to 10. N1 Q hat 1 is greater than or equal to 10. So those numbers, let's check that one first. So 415 over 223 over 415 is greater than or equal to 10. So that's definitely checks out. Whoops, I'll say. And then 415 times Q hat. Q hat here would be 192. These cancel, these cancel. So 192 is greater than or equal to 10. And we have to do this for the other sample that we got. So that sample size was 630, and that P hat was 317 over 630. That equals 10. And 313. And we can see both of the normality conditions check out. Okay, great. Now, independence, we're drawing from two different populations here. So it's reasonable to assume, because they were taken at different times, that both samples would be independent from each other. And also it's reasonable to assume that there are more than 400, 1,050, and 6,300 potential voters in both populations. So let me write that down. So for independence, since actually, that's right, both samples would be independent as they are taken from two different times, or they're taken at, not from. That doesn't make sense. They're taken at. And it is reasonable to assume there are more than 4,150 and 6,300 potential voters in both populations. All right. So really not much different than we've done, except maybe the normality condition's a little different. So now, again, with calculation, this is by name or formula. So the name is the 2-prop z-ins. The formula is going to be z equals p hat 1 minus p hat 2 over. Now, this formula, like I said, is a little different. It's p hat c over n1 plus, sorry, actually no, whoops, little mistake there, sorry. It's p hat c q hat c over n1 plus p hat c times q hat c all over n2. So now what the heck is this p hat c? Well, this p hat c is pooling, basically. So you're averaging the combined proportion. And again, it's not really an average, because you take the count of your successes and then you divide it by the total in each population. So it's not really a straight average here. So you get 540 over 104, 1045, which is equal to 0.517. Okay, so if you plug in the formula, this would be z equals 223 over 415 minus 317 over 630. And now, again, this is the p hat combined. Is that exact or did I round that? 540 divided by 1045. Yeah, I rounded that. Okay, I rounded that to 3 decimal places. Okay, so then you would do 0.517 times 0.483 over 415. Plus 0.517 over 0.483 all over 630. Okay. Now, that test statistic comes out to 1.08. All right, so now let's go to the actual calculator right now and see what this is all about. So we're going to go stat, test, and we're going to do 2 prop z test. Okay, now x1 and n1. x1 is the numerator of the first proportion. So the numerator of the first proportion is 223 out of the total 415. x2, the successes, is 317 over 630. Now, we are saying that p hat is greater than p2. So we are correct to pick the third one there, and we're going to calculate. Now, I want to show you what it outputs. First, you see the test statistic, which we calculated. That's your p-value, a high p-value. They give you your p hat 1, so that was the sample proportion from the first population. P hat 2, the sample proportion from the second population. This p hat, and they don't put a little subscript c, but that subscript c, this is p hat subscript c. And then you can see they correctly show you what your sample sizes are, and that's it. So from here we have, and let's write this down. If we were to sketch out our sampling distribution, and again, this sampling distribution, you would assume that it's centered around 0, because these are, the sampling distribution is based on p hat 1 minus p hat 2 being very close to 0, because you're saying, you're testing the claim, like, is there really a difference between the proportions after these remarks have been made? If there's no difference, most of them will center around 0. So these are p hat 1s minus p hat 2s. This is our sampling distribution. So the normality condition up there, when we say that normality is what the heck word am I looking for? This is when I need you guys. It's satisfied. There we go. The normality is satisfied. We're saying that the differences are sample proportions in our sampling distribution would be approximately normal. So I'm just going to get rid of those little p hat things. But, okay, so we got 0. And our test statistic, whoops, that's a little low considering such a high p-value, 1.08. So, and you're shading greater than. So greater than would be there. And what do we get? So you could say the probability that z is greater than 1.08 was our p-value of, what was our p-value? I think it was close to, let's just look. Do I still have it on? Yeah, so 0.14. So this is about 0.14. And I also want to, I just thought of this. You could write the null and the alternative as P1 minus P2 is equal to 0, and then P1 minus P2 is greater than 0, which then would make more sense probably to you guys if this is based on P hat 1 minus P hat 2 being close to 0, and you're shading the red because it's greater than 0. Just kind of thought of that right there for some more clarification. All right, so high p-value, alpha is 0.05. What does that mean? We're definitely failing to reject the null. So we're going to say since our p-value is greater than our alpha level, our findings are not statistically significant. Okay. We fail to reject the null. Now, what does this mean in context? Well, what this means in context is that there isn't enough evidence to support or to show, either one. There isn't enough evidence to show a decrease in voter support after the unfortunate remarks. Okay. I think they called it unfortunate remarks, right? Did I say unfortunate remarks? Let's see. Yes, unfortunate remarks. Okay, so that's a 2-prop z-test, and hopefully you followed along with me. You obviously can ask me any questions. I am going to do another video that does the next FRAPI to show you how to do a confidence interval, but I'm not going to include it in this one because it's 3:10 and I have to go get my kitties. So I will see you guys tomorrow. All right, have a great night. Bye.